bus, the clock, and the general purpose registers of bb0.2. So first things first, let's go ahead and kick bb off by hitting Control K and enabling the simulation. At a luxurious 8 Hertz, we are going to load in the program. In this case, it'll be our lovely infinite add that we saw in our introduction video, and this time we'll be counting in 2s. So this whole layout here that we have is, as you could probably tell, is very much built up from, it's built organically. There was no looking ahead. I didn't know what I was getting myself into. So everything is kind of hunked in wherever it can fit. We've done a lot of cleaning up, actually. All of these control lines used to have to live and splay out over this whole space, and I intended to kind of take bb0.2 as a shell, and I've really just eliminated that. So fear not. All of the sort of messiness of this is definitely much improved later on down the line. So the clock, really the only notable thing about the clock is that it sits behind this control buffer. This control buffer is the inverted signal coming from our halt control line. So whenever we want to halt the computer, we absolutely can. We can just light up that control line. As soon as that control line goes high, the inverter inverts that into a low signal, saying that this control buffer no longer is outputting the value of the clock onto the clock line. In essence, this shuts the computer down, or really just freezes it where it is. Nothing can happen now. The halt line can't be turned off, because in order to do that, the computer would need to move forward to the next microcode instruction by taking the next clock down and loading it in. But the clock will never go up or down again, and the line is left floating. So none of the components can do anything when that clock line is floating, because they all rely on the clock going high or low in order to accomplish some part of their task. The 8-bit bus is really just that. It's a wire that connects everything together that needs data. There's only one data bus. It's also used for instructions. In other computers, there is an instruction bus and a data bus and multiple different buses all over the place, and that's something we experiment with a lot in bb0.3. But here we just have the one. It's the Ben Eater style 8-bit computer, so we only have the one data bus, and that centrally connects everything together. We have this lovely LED bus monitor over here that can kind of show you what's going on, and we only have the binary interpretation because anything else would just kind of be too much work and not enough payoff for that. So with those out of the way, we can take a look more closely at our general purpose registers. This will give us a detailed look too at the registers in general and how each of them is designed. So let's look at register A and open it up and go ahead and see. We can go into one register here. So this is our one of our registers. And this is literally storing 1 bit of data. So this right here is our D flip-flop, and this is chosen because this is what we used in the Ben Eater videos. So this is a built-in component. It really is just, it was too fiddly to try to work with the electronics of the D flip-flop. Building them custom, you can try to do things like that in Logisim. I did not feel like it, so I didn't. So this clock is pulsing away. And this system of circuits is what allows us to figure out exactly what we're storing inside of our flip-flop here, which at the moment is nothing. So we, in order to look at this in more detail, I would really suggest to go look at the videos. So if we go over here, I don't know, what are we currently holding right now? Oh, okay. So, okay, yeah. So let's go over here and we know that we know this one's going to be changing at some point. Aha, so we've arrived at something that actually holds a value. Ah, it's back over here. So this is actually, if we look at this for long enough, this should pulse back and forth because it is the first bit. You know, it doesn't particularly matter. So that's what's going on here. Now, the load, which is to say write, so whenever we want to write to the registers, we bring this line high. That is going to bring every single one of these into writing at the exact same time. So once this line goes high, the next time the clock pulses high, it'll take the value on the bus and input it into each of these registers in turn. So the 0 register here, that comes here, 0, 1, 2, 3, 4, 5, 6, 7. As explained already, we have these controlled buffers. They're all tied to this enable line. So when this enable line goes high, all of the 8-bit value gets put out onto the bus. So it's very important that they be synchronous. Now, the enable does not rely on the clock at all. As soon as the enable line goes high, it puts its value out onto the bus. And it's left up to us, the programmer, to make sure that nothing is that two things aren't trying to put two values on the bus at the same time. That results in most of the time just flat out errors, but sometimes you can just get into weird situations where there aren't any errors, because really the conflict is when we're trying to set one of those bits to 0 and 1 at the same time. That's a no-no. That's a problem. So as long as that's not happening, there might not be an error, but subtle weird things can go wrong, and inevitably it'll mess everything up. So that's one of the things that we have to really carefully think about and monitor when we're building our assembly code instructions, that we're not allowing at any point for two things to go out into the bus at the same time. It's always a risk that we run. So if we go back to our main circuit, we see that we only have the A and the B registers. The A register is used for a lot of things. The A register, or really it's only used for a couple of things. It's used for a lot in terms of it is the most used register in the assembly code instructions. When we want to output something, we use the assembly instruction out. And it just takes whatever's in the A register and puts it into the output register. So they're general purpose because we really can put anything in there, but also the computer itself has many uses for these registers. So if we want to make sure that a value is preserved over time, we can leave it in the A register if we want to be careful to never overwrite that with something else. So whenever we perform an add instruction, we take the contents of A and B that are already summed in the arithmetic logic unit. We let the ALU go out onto the bus, and we write into register A. So if you cared about what the value that was in the A register before you did the addition, you would need to store that off into RAM before you do this operation. So this is the kind of thinking that I've really started to learn how to employ. I really have enjoyed building this up, and like I said in the last video, these custom-made components are all well and good for learning, but in terms of learning how to go to the next step, the next level of accessing all the memory we can, these registers really just need to be the built-in components. They're more efficient than anything else. Just to give you a sense of the scope of what it would be like to scale up our custom-built registers, the 8reg has been used for all of the registers that we have here in bb0.3, or 0.2 rather. So there are 11 custom registers, which means there's 88 1reg chips with 1 D flip-flop apiece. So that's 97 total components, and that's not including the wiring, but just in those components alone that we just pointed out, the 88 1reg chips, and then the 11 components that store them, the 8reg chips. That's not counting all the wiring and stuff. All of that has to get written to an XML file and manipulated in memory by Logisim. And for whatever reason, Logisim does not handle scaling up with that very well. We'll see that actually come up in a lot of places. And it's one of those disappointing things where we very rarely get the opportunity or the chance to really go full hog with some of our memory things that we might be able to, thinking, well, we're running on a modern computer, but the program itself limits us in how it deals with all of these things. So it creates a limitation, but restriction breeds creativity. It's one of my favorite sayings from the head designer of Magic the Gathering, Mark Rosewater. And our restrictions are numerous here, but they're really a different set than the ones that Ben Eater had making his 8-bit breadboard computer. And for everyone that's doing the actual physical manifestation of the Ben Eater style computer, those problems are inherently different. We are all facing the same problem of trying to compute, but in Logisim we have a different set of restrictions and limitations, and some things are significantly easier and some things are not at all. So that's one of those things that we're just not going to be able to scale up with, is our RAM. We can't just put our 8, and in that count I actually missed out. I'm reading this now. We missed out on the 16 chips inside of RAM. The RAM is custom made as well, and all of those are 8regs as well. So, I don't know what that math is right off the top of my head. Well, let's go ahead and... So that's, I just did the math, and that's 241 components that that the Logisim has to keep track of, not including the wiring. Again, I don't really care about the wiring. And we can actually pull up statistics inside of Logisim, but that's kind of beyond the scope of this video. So yeah, that's been a brief tour. So yeah, this has been a look at our registers, our clock, and our data bus line. Join me in future videos as we continue to work through all the components of bb0.2 before finally starting to look at the build process for bb0.3. So be sure to hit subscribe if this is content that you enjoy, and go ahead and give me a little like if that's if this is something that you found useful. Feel free to please check out Ben Eater's videos in the description. Without Ben, none of this would be possible, and as always, we give a big shout out to him. So thank you very much, and I look forward to seeing you in the next video.